once we have these definitions, a very important idea in group theory and physics especially is the idea of the little group. So the little group has many names. It's also called the stabilizer. So the little group, the stabilizer. Sometimes it's called the stabilizer, sometimes it's called the stabilizer group. So I'm going to put the group in a bracket. It's also called the isotropy group. So isotropy group, not to be confused with isometry group. Okay, so these are the different names of this guy. So what is the little group? So let G be a Lie group, that acts on some manifold n. So the little group or the stabilizer so of a point, of a particular point, say P, of that manifold is the subgroup, defined by its HP. So the subgroup depends on the point that we choose. It's generated by it's given by all the elements in G, such that the action of G on P is a fixed action. Okay. So note that for the stabilizer to be non-trivial, the group action must have been fixed points, right? Otherwise, it won't be, the H group won't be a proper subgroup. So can somebody give me an example of a stabilizer group? Again, so there is some group G, it acts on some manifold M, there is some point P on this manifold, and there's a subgroup of G such that when elements of that subgroup acts on P, it doesn't change P. You can show that that subset is actually a group, a subgroup. And that subgroup is called the stabilizer group. So can someone tell me an example of a stabilizer group from one of the examples we discussed today?
Sir, SO3Z of the true sphere, the North Pole.
SO2Z.
Yes, sir.
Yeah, exactly. So if I take the two sphere and take the North Pole, then of course what I've been calling SO2Z, they don't change the North Pole, right? And you can show that that is a subgroup. So it's not immediately clear that this is a subgroup, but you can show that H satisfies all the axioms of a group. And therefore it is a subgroup. Okay. Okay, any questions? Okay, let me just explicitly say what, who was that who answered that question? I didn't look at that list. I wasn't looking at that. Was it Zabir or?
Sorry, it was Fahim.
Sorry?
Fahim answered that.
Oh, Fahim, yes, okay. Thank you, Fahim. Yeah. Okay, yeah. Fahim Ferdowsi. So, so let me just explicitly, say what Fahim was saying is that, say, take S2. So let us take S2. And say the North Pole is a point which, if I use, say, the Cartesian, well, it doesn't have to be the North Pole. Let's just take this, this point. So I'm using the Cartesian coordinates. It should be clear that P is a point on the two-sphere. And then if I look at all the SO2s, which are of this form, SO2 matrices, which are of this form, cosine of theta, minus sine of theta, sine of theta, cosine of theta, right? So this is an SO2. These are SO2, which is a subgroup of SO3. So this SO2, this is the, it's an example of an invariant subgroup, right? Very good. So there is a theorem, and I'm not sure if I want to prove this theorem today because I want to go into the details and take my time. So what I'll do is that I'll probably prove it at the beginning of the next class. But the theorem is called the orbit stabilizer theorem. So it's called the orbit stabilizer theorem. And what I'll do is that I'll give you an example of this theorem. And what you can do is that you can just like maybe work it out yourself or think about it yourself before the next class, so that when we talk about the theorem in general, you have a better sort of intuition about it, okay? So the idea is something like this. Suppose you have some group G, acting on some manifold M. It doesn't have to be a manifold. It's actually a much more general theorem. It also works for discrete groups and finite groups. So now suppose H of P is a stabilizer group. Okay, so for say for some P in that manifold. Okay, then the coset space of H of P, because if you have a subgroup, you can always make a coset space, right? So the coset space is then, there's a map between, one-to-one map between the coset space and the manifold. You can identify the coset space with the manifold. Okay, this is not a homomorphism because M is not a group, but they can be identified. Okay, so this is the orbit stabilizer theorem.